Building a speech recognizer used to demand thousands of hours of audio that humans had painstakingly transcribed word by word. That labeling is slow and expensive, and for most of the world's languages, it barely exists. Then Meta released Wav2Vec, and later Wav2Vec 2.0, which flipped the recipe. The model learns the structure of speech from raw, unlabeled audio first, and only then needs a little labeled data. Today, we're breaking down how that works. Let's walk through the recipe one stage at a time. First, a convolutional encoder reads the raw audio and turns the waveform into a sequence of latent speech features. Think of it as compressing a long, messy signal into a tidy row of vectors, where each vector captures what's actually happening in a short slice of the sound. That row is what everything downstream will work with. Then, the model hides some of those time steps, masking them out much like bird hides words in a sentence. The network can no longer see what was there, so it's forced to reason about the missing stretches purely from the audio surrounding them. That pressure is what drives it to learn. Next comes the clever part, a contrastive task. For each mask spot, the model must pick the one true quantized latent out of a lineup of distractors. Getting that right forces it to learn phonetic structure, the real building blocks of speech, and it does all of this without ever seeing a single transcript. Finally comes the fine-tuning. On top of all that self-taught knowledge, you add a small amount of labeled audio, and a strong recognizer emerges. Remarkably, as little as 10 minutes to an hour of labels can be enough to get real, usable accuracy out of the system. Now, here's the shift that matters, laid out plainly. Traditional speech recognition is fully supervised. Every hour of training audio needs a matching human transcript, and you need thousands upon thousands of those hours. For a widely spoken language, that's merely expensive, but for a low-resource one, it's often simply impossible to gather it all. Wav2Vec splits the problem cleanly in two. It pre-trains on a mountain of cheap, unlabeled audio to learn how speech is actually built, then fine-tunes on just a thin sliver of labeled data. The heavy lifting happens before anyone transcribes a single word, which is exactly why the labeling bill shrinks so dramatically compared to the old way. Let's pull out the 3 ideas that make Wav2Vec work. Pre-training without labels is the foundation. Using a contrastive objective on raw, unlabeled audio, the model teaches itself useful speech representations from nothing but sound, no human annotations required at all, which is what the self-supervised label really means. Mass prediction is the trick that borrows straight from BERT. By hiding chunks of the audio and forcing the model to recover their identity, it learns the phonetic patterns that make speech intelligible, the same way a language model learns grammar by filling in blanks. Data efficiency is the payoff, and it's a big one. After pre-training, a genuinely strong recognizer can be fine-tuned from very few labels, which is exactly what makes high-quality speech recognition feasible for low-resource languages that never had thousands of transcribed hours to begin with. Okay, let's lock in the essentials. Wav2Vec from Meta brought self-supervised pre-training to speech, so you no longer need thousands of expensive, hand-labeled hours just to get started. The newer version, Wav2Vec 2.0, masks time steps and uses a contrastive task to identify the true latent among a set of distractors. After pre-training on unlabeled audio, fine-tuning on just a little labeled data yields a genuinely strong recognizer. As little as 10 minutes to an hour of labels can be enough, which opens the door for low-resource languages. Craving more AI ideas made simple? Head over to Standarity.com. See you in the next one.